My name is Nguyen, and I'm at the Turing Institute here in London, and I'm also affiliated with Edinburgh University. So I'm going to talk about using natural language processing to study social phenomena and to help the social sciences. But before I'm going to do this, I'd like to give you a very short introduction to the Turing Institute. So who of you actually knows or have heard about the Turing Institute before? Okay, well, it's actually not bad. So the Turing was founded in 2015, and it's the UK's new national centre for data science. And so we're based at the British Library, and we have 5 founding universities: Cambridge, Edinburgh, Oxford, UCL, and Warwick. And that means that a lot of the students or researchers based at the Turing are also affiliated with one of these universities. So we have PhD students, we have research fellows, we have a lot of faculty affiliated with the Turing, and also we have visiting researchers and interns, and we have a lot of public events. So almost every week there are seminars, tutorials, as well as talks. So if you're interested, most of them are available for the public to attend. I recommend checking out the website. So I'm interested in how we can analyze data on a very large scale to study social phenomena. But to motivate this, let's go back to some traditional data sources that are typically used in the social sciences. For example, surveys are still frequently used. Another way is observations, going into a country, talking to people, getting to know community, or having interviews. And these are very valuable methods. A lot of times they give you a lot of information about the people that you're studying, but also it can take a lot of time. So sometimes it can take multiple years to collect this data. And then the sample that you end up with is still relatively small compared to the samples that data scientists or computer scientists are used to work with. Maybe even a bigger problem is what in linguistics, for example, has been called observed paradox. So a lot of times you are interested in analyzing people's language or behavior when they don't know that they're being analyzed, right? If you give them a survey or if you interview them, you have the risk that they adapt their response to what they think the researcher likes to see. And this is a really challenging problem, and that's why I'm very excited by all kind of new types of data that are becoming available, like social media data. So social media data is very large, but also the nice thing of social media is that a lot of people are not really aware that the data might be used for social science. And so we have a lot of interesting language. Also, we have very fine-grained interaction patterns. So we often have social network structures. We can see who's responding to who. Increasingly, we also have data over time. So sometimes we can even track an online community and how it evolves over multiple years. And also we have increasingly multimodal data. So not only text, but also photos, videos, and speech. Of course, there are also many challenges. One, for example, is that artists are most of the time anonymous. We don't know who they are. Most of the time, we don't have their social demographic information. And also, it often involves repurposing data. So we're using data, for example, from a social media platform that was not designed specifically to collect this data. For example, if you want to use Twitter to estimate public opinion, Twitter was not designed with this particular goal in mind. So I'm interested in social media, and it also raises a lot of challenges but opportunities when we analyze language. So in natural language processing, a lot of the tools or research has focused on language that we find in, for example, newswire text. And this is the kind of language that is very standardized, right? So this is a piece of text in the Washington Post in 2016, where Leonardo DiCaprio finally won his Oscar. And then if you look at tweets about the same event, and posted on the same day, you see that the language looks very different, right? So these are tweets by LL Cool J and Oprah Winfrey. And for example, Oprah Winfrey, she says, "It happened," and she's repeating this P. And then she says, "Bravo, Leo, standing O in my PJs." And so it's not that Oprah Winfrey doesn't know how to write happened, right? She's probably doing this on purpose. She's doing this to connect with the audience, maybe to emphasize that finally Leonardo DiCaprio won his Oscar. But the main point is that this type of variation in language is actually very meaningful, because by analyzing this variation, you can learn more about people's backgrounds, about their beliefs, about their social relationships, and that's kind of the language that I'm interested in. So my research is on doing large-scale analysis of text to study social phenomena. And so I'm doing this mostly from the viewpoint of social linguistics, which is a field in linguistics that studies the relation between language and society. But I'm focused mostly on using computational approaches. And if you're interested, together with a few other people, I wrote a survey article on this topic. So yeah, if you'd like to know more, then you could take a look at this article. So there are a couple of benefits of doing this kind of research. First of all, it could lead to more fine-grained analysis of online behavior. For example, by analyzing people's language, we can learn more about their demographic backgrounds. And this has a lot of applications in industry as well, related to, for example, user profiling. Also, we can develop more robust NLP tools. A lot of the natural language processing tools have problems with slang, informal language, dialects, etc. And so this is also another big area of research. What I'm going to talk about today are the final 2 points, is using natural language processing to test social science theories on a very large scale, and also developing new analysis tools that linguists and social scientists could use. So this is the first example that I'm going to give, and it's about the Movember campaign. So who of you have heard of the Movember campaign? Okay, a lot. So it's this campaign targeting men's health. It runs in the month of November, and a lot of people know it because it encourages men to grow a mustache, and then you can support them by donating money. And the campaign traditionally focuses on cancer, but also more recently on mental health, for example. So the interesting thing is that a lot of people sign up to participate in the campaign, but then if you look at the amount of money that people raise, you see that sometimes some people raise no money at all, and some people raise a lot of money. And so for both the Movember campaign as well as for social scientists, it's interesting to understand why some people raise more money than other people, right? Because if you understand this, you could potentially also make the campaign more effective. And so this was a collaboration with social scientists at my previous university in the Netherlands, and also with the Movember campaign. So in the social sciences, there's this particular theory called the social identity model of collective action that proposes that the reason why people participate has a big impact on the outcome. And if you think of the Movember campaign, then there are 3 different motivations according to this theory. The first one is the injustice motivation. And so in the context of the Movember campaign, this means you had cancer yourself, for example, or you know someone who had cancer. The second motivation is what they call the social identity motivation. This means that you participate in the campaign because your friends are participating, or you just want to have an excuse to grow a mustache. And the third motivation is what they call the collective efficacy motivation, and that means that as a group you can make a difference. And it's also important to realize that these different motivations are not mutually exclusive, right? So someone can have multiple of these motivations. And what we wanted to do was, well, can we automatically analyze or identify these motivations and see if it indeed has some relation with the amount of money that people raise in the campaign? And the nice thing of the Movember campaign is that people who participate have a public profile. And in this profile, there's this text box called My Motivation, where people explain why they participate. So what we did was we first sampled a set of profiles, and we manually annotated these profiles according to these motivations. And then we trained supervised classifiers to automatically identify these motivations and apply it on a large scale. So because these motivations are not mutually exclusive, we trained binary classifiers for each motivation. So for each motivation, we would be able to say whether this type of motivation was present in a text or not. And we used a very simple model, logistic regression, with all kind of text features as well as topical features. And this is the F1 score that we got. And these are some of the features that were most predictive of the motivations. So, for example, the injustice motivation was characterized by words like cancer, friends, lost, and father. The social identity motivation was characterized by words like fun, team, or mustache. And the collective efficacy motivation had words like change, awareness, yourself, etc. And so what we then did was we applied these classifiers on over 90,000 profiles of these participants, and then try to analyze to what extent it related to an amount of money that people raised. And we found that participants with an injustice motivation indeed raised significantly more money than the other participants. We also found that participants with a social identity motivation were more likely to be part of a team. And if they were part of a team, they also raised significantly more money. So this is just an example where we have a social science theory, and then we want to apply it on a very large scale, and we're using natural language processing to train these methods to do this automatically. The next example that I like to give is how we can use natural language processing or machine learning to build new analysis tools for linguists and social scientists. And so this is a study about dialects, about how people in different regions talk differently. And in the study of dialects, a key step in many analyses is identifying a set of linguistic features that exhibit regional variation. And with linguistic features, I mean different ways of referring to the same words. For example, in the United States, we have soda, pop, and Coke to refer to the same soft drink, for example. But you could also think of just relative frequency or the presence of a particular word. The problem is that in linguistics, traditionally, a lot of the research was based on manually identifying these features. And for this, you need to have a very deep knowledge of the region and the language. But also, it means that sometimes you might miss interesting features that you don't expect. And it also makes it more difficult to reproduce this research because it's so dependent on the knowledge of the researcher. Another problem is that we have all this data now, and so we could potentially analyze thousands and thousands of words. So manually selecting them becomes very difficult. So this is just an example of the data that we have. So this is based on Twitter data, the plot on the left, where the color in each region indicates the relative frequency of referring to French fries in the Netherlands. So in the Netherlands, there are two different ways of referring to French fries. And just looking at the plot, it looks like people in the south tend to use a different word than people in the north. And this is a pretty clear pattern, but a lot of times the pattern is not as clear, right? And it's really difficult to manually say whether there's really a significant pattern going on or if it's just random. So what we want is to have a statistical method that can tell you where there's a dependence between x, the feature values. So this could be the presence or the absence of a word or the relative frequency, and y, the locations. And so the locations could be GPS coordinates, for example, if we are working with tweets. And so the null hypothesis would be that there's no spatial dependence. And what we would like is to have a method that's able to really exploit fine-grained location information. So if we have GPS coordinates, we want to use GPS coordinates. It should also be applicable to all types of data, binary data, categorical data, and frequency data. And also it should be able to detect nonlinear dependence. So this is a method that was used or introduced in 2011 by Grief et al. To the linguistic community to do this kind of testing. And I'm going to explain it just to understand the limitations that this method has and why we use the different method. So they use Mo&Zi, which has existed for much longer, but in 2011 they applied it to linguistic data. And so the first step involves aggregating observations into bins. And for each bin, calculate the relative frequency of a feature. So for example, in the Netherlands, you have different municipalities. And then for each municipality, you would aggregate all the tweets that you have and calculate the relative frequency of a particular word, for example. The problem is that besides municipalities, you could also decide, well, maybe we should look at provinces in the Netherlands, right? You need to make this decision of which level you're going to look at. The second step is calculating a spatial neighborhood matrix W, which is just the pairwise distances between each bin. So for each municipality or each province, you would calculate the distance. And if it's below a certain threshold, you would give it the value 1, and otherwise you would give it the value 0. And so you would end up with a matrix with all these values. And then Mo&Zi is just the covariance between the points that are spatially similar, so for which W values are 1. divided by the total number of points that are spatially similar, and then you divide it by the total variance. So it's a very effective method, but it has some limitations. First of all, it requires the use of bins. So you need to decide beforehand, are you going to look at provinces? Are you going to look at municipalities, for example? Or in the United States, are you going to look at states or counties, etc.? Maybe a bigger problem is that it's insensitive to the number of observations in a bin, right? For some regions, you might have only a few data points, and your estimate might be very noisy, where for some other bins, you might have lots of data points. And ideally, you want to take this into account. It also relies on this weight matrix, which means you need to decide on this threshold that you're using. And also not suitable for linguistic features that have more than 2 variants. So because you're dealing with relative frequencies, something like analyzing soda, pop, and Coke in the United States wouldn't be possible with this method. So what we use is called the Hilbert Schmidt independence criterion, which was introduced in the machine learning community in 2005. And I'm just going to give you a high-level overview of what it does, and feel free to ask me afterwards for more details. So if you have 2 random variables, x and y, and if they are independent, then the covariance is going to be 0, right? So if you look at the plot on the left, there's a clear dependence between x and y. And so when you calculate the Pearson correlation, it's going to be very high. And the Pearson correlation is just a covariance normalized by the standard deviations. So if you look at the plot on the right, there's also a very strong dependence between x and y. But in this case, the Pearson correlation is going to be close to 0. And the p-value is not going to be significant. And that's because this trend is not linear. But if you would calculate the Pearson correlation between x squared and y, you would get a very high correlation. So the idea is that sometimes by transforming the data, you can detect dependencies that otherwise you wouldn't. So HSIC, it was proposed by Gretton et al. In 2005, builds on this idea. And you could think of looking at covariance in a very high-dimensional, potentially infinite-dimensional space. And in this way, you can detect dependencies that you wouldn't otherwise. And the nice thing is that it's suitable for all types of data. So you can apply it to binary data or categorical data, frequency data. So some of you might be familiar with kernel methods, where you map individual points to a high-dimensional space. So this is just a generalization of this idea, where you map a distribution to a point in high-dimensional space. Right, so here you have this random variable x, and you map it to this high-dimensional, potentially infinite-dimensional space. And then in the space, you're going to calculate your test statistics, which is going to tell you where there's dependence or not. So if you want to test whether 2 distributions are the same, what you would do is map these distributions to these points in this high-dimensional space. And then you're going to look at the squared distance between these 2 points. And if they are the same, the distance is going to be 0, and otherwise it's going to be bigger than 0. And the nice thing is that if you're using a kernel that is characteristic, it means that mapping distributions to this high-dimensional space is going to be injective. So different distributions will be mapped to distinct points in the future space. And so if you want to test for independence, you could do the same thing, but then you're going to look at joint distributions and the product of the marginals. But then you're doing this in this high-dimensional space, and that's called the Hilbert Schmidt independence criterion. And there are a lot of references and tutorials online also, if you're interested in this. So one challenge that we had was, well, we have this interesting method that we want to apply to linguistic data, but if you just have Twitter data, for example, we don't have a ground truth. We don't know the right answer, right? So how can we compare this against other methods? So that's why we first generated syntactic data, for which we simulated geographical patterns in the data to test whether methods were able to identify it. So this is an example of variation from east to west in the Netherlands, where you see this pattern going from east to west. And so what we did was we varied the amount of data, and then we looked at, well, whether methods are able to identify whether there was a significant geographical pattern. And so HSIC, the one that I just discussed, is the green line. Mo and Zai, that I also discussed, is the blue line. And then we also compared against 2 other methods. And so the power is just a fraction of simulations for which the approach is correctly rejected in a hypothesis. So for each particular setting, we ran multiple runs, and we computed for how many of these runs these methods identified some significance. And you would see that HSeq performs pretty well, and that as the data increases, so if you go to the right of the plots, the methods also perform better. So if you have more data, it's easier to detect significance. So we also applied HSeq to Twitter data in the Netherlands, just to identify new words that have a strong regional pattern. And the top words that we ended up with were all city names, which is not surprising. But the next step that we, of course, want to explore is, well, can we filter out these names and only keep the interesting words for linguists, right? So, because for linguists, it's not interesting that a particular word like Amsterdam or Groningen has a really significant regional variation. You want to automatically identify words like soda, pop, or coke, etc. So this was published in last year in Computational Linguistics. So if you're interested, take a look at this paper. So now I want to discuss a few challenges. So I've given 2 examples of how we can use natural language processing to support social science research, but also a lot of challenges. And I don't have time to address all of them. So I'm just going to discuss 2 of them based on my own interest and my own research experience. But there are many more, including a lot of ethical challenges that I am also happy to talk about later if you have questions about this. So the first one is about data. So I started the talk with, we have a lot of exciting data to study social phenomena, but of course there are also many challenges. For example, in academia, but also in industry, a lot of the work has focused on Twitter, because Twitter data is relatively easy to collect. It has a really easy API. And for example, Zeynep Tufekci even calls Twitter the model organism for social media studies. So for example, in biology, there's a lot of work focusing on the fruit fly Drosophila, and then they hope that what they find by analyzing the fruit fly also applies to other species. And you could say the similar thing to Twitter. A lot of people focus on Twitter, but I think we have to be really careful with what we conclude from these findings, because different platforms, they have really different mechanisms that shape user behavior. They have different community norms of what kind of content is appropriate. They have different user demographics, etc. And so ideally, we would like to see more research, not only focusing on Twitter, but also other types of data, and also research that compares these different data sources. Another problem is really biased user demographics. So this is data from a few years ago, and I think it has changed. But this was a very fine-grained annotation of Twitter users in the Netherlands. And we really annotated age, for example, on a very fine-grained scale. And you would see that the age distribution was very skewed towards younger Twitter users. But maybe a more interesting observation that we also had was when we looked at the different age categories and how gender was distributed. We found that the younger age category, there were more females, and the older age categories, there were more males. But this means that if you're doing certain analyses, you need to control for both gender and age, because otherwise some of your analyses might have some confounding patterns. For example, you might see that particular words or particular linguistic features or behavior are used more in the older age categories, but actually it might just be associated with males. Another example that I'd like to give regarding challenging noisy data is Google Books. So Google Books has been really popular also, for example, in digital humanities. It contains a really big collection of books in multiple languages. It has this web interface, and you can also download the data. So it's really accessible. And so you can do all kind of interesting, or you can make all kind of interesting plots. So you can see how words change over time. But what I actually want to ask you is, well, do you have any idea of what we're seeing here? Because, I'm sorry?
Less books.
Books?
Less books. Less data.
Less data. Oh, No, but why in this region particularly? Because this is what you wouldn't expect, I guess, right?
Have another meaning?
I'm sorry?
Had another meaning.
Had another meaning? No.
In the archive, the old books.
Default value?
So, during that region, during that time area, people used the long S, and OCR confuses with an F. Oh, yeah. And so there are a lot of like blogs and websites if you like to see more of these examples. But the main thing is that sometimes you see patterns in the data, and if you don't go back to how this data was created or what is in the data, you might see something that you don't expect, or you might draw incorrect conclusions.
Oh, sorry. So this is like the graph or the word fog, is it? Or
Yes.
Oh,
You can try. Yeah. You can try it online, and then you can also enter all kind of other words if you're interested. Okay, so another example that I'd like to give is Urban Dictionary. So I'm very interested in online language, and together with a few colleagues, we were interested in, well, how do new words emerge, or how do new meanings emerge? And so we started looking at Urban Dictionary, these online crowdsourced dictionaries. And what we did was we collected the data from December 1999, the beginning of Urban Dictionary, until July 2016. And what distinguishes Urban Dictionary from many other dictionaries is that for one particular word, you can have multiple definitions, right? In Wiktionary, each word has only one page, but in Urban Dictionary, users can just contribute their own definitions to what they think the word means. And so if you look at the words that have a lot of definitions, for example, emo has over 1,200 different definitions. And I would say that just by looking at the top words, I think it already indicates that Urban Dictionary is a very special dictionary. And so we had all these ideas of linguistic analysis that we wanted to do, but we thought, well, we first need to understand what is actually in Urban Dictionary. And if you look at Urban Dictionary, you notice, for example, that a lot of the definitions are actually opinions. People providing an opinion about a particular concept or about a particular person. And so we annotated this data. Yeah, so these are the results. So what we did was for each word, we mapped it to a frequency bin based on the number of entries that the word had. So some words had only one entry, one definition, so they appear in the lowest frequency bin. And some words have hundreds of different definitions, so they appear in a higher frequency bin. And then we calculated, we sampled words and their entries for each frequency bin. And then we annotated it using crowdsourcing, whether these entries described an opinion, meaning, or both. And the left plot shows you all the entries that are not describing proper nouns, because in Urban Dictionary we also found that a lot of entries were about people, about places, and about names. And so these are proper nouns. But the left plot shows you the results based on entries that were not proper nouns. And you see that for higher frequency bins, the percentage of opinions tends to increase. And if you look at the plot on the right, so these are entries about proper nouns, so entries about names and places and brands. And there you see also that the proportion of opinions is much higher, and also that it tends to increase as you go to higher frequency bins. For example, in frequency bins 8 and 9, the proportion of opinions is almost half of the entries that we sampled. And this is a really clear difference between what you would see in many other dictionaries, where they usually have a clear guideline that the content has to be objective. So this was the first challenge that I want to discuss. So sometimes we really need to spend lots of time understanding the data and how the data is created before we can do more analyses. And also, an important point to take away, I think, is that biases can be introduced in the complete research process. So when we select the data that we're using with, the way we sample the data, the way we process the data, etc. And also, to what extent the bias is a problem for your research, of course, depends on your research question. So the second challenge that I want to discuss is differences between natural language processing and the social sciences. And of course, this is a very simplistic view. But in natural language processing, a lot of the work that is done focuses on task, right? We try to automate a task, and a lot of the evaluations are, for example, based on accuracy or F-score, precision or recall. And so you could say that natural language processing is very task or very performance-driven. In contrast, in the social sciences, it's much more insight-driven. We want to learn more about a particular phenomenon. We want to build or test a particular theory. And for example, in social sciences, a lot of the models are only using a few variables. Well, in natural language processing, we often have thousands and thousands of features. And one way, I think, to try to bridge this gap is by making these natural language processing models more interpretable. And I think this also has a lot of industry applications because these black boxes are very difficult to work with in many different settings. So I think with more interpretive models, we can use them for theory building and explanation, but also they can help us in how to formulate a particular problem. Because sometimes when we work with social scientists, the concepts or the problems they work with are so abstract that it's very difficult to clearly define it. And then if you iterate it, you might narrow down your definitions. And if you have an interpreter model, this can help you do it. Also, it can support error analysis and feature discovery and help you to review confounding features. So I just discussed all kind of biases that we have in the data. And a lot of times when we have biased data, if we learn a machine learning model, this machine learning model might pick up on these biases. They might use certain features that we don't want them to use. And so if you have an interpreter model, you can analyze what's going on and potentially correct these models. So, for example, in the social sciences, approaches that are still frequently used are word list or dictionary approaches, which means that you have a list of words, for example, indicating positive sentiment, and then you have a text and you calculate the proportion of the words in your text that are in this list. And this is very transparent. It's easy to change, it's easy to add or remove words, but also it isn't very powerful. So it has problems with sarcasm or negation, etc. We also often use linear classifiers, for example, logistic regression and linear regression. They can use thousands of features, which already increases the difficulty of interpreting the models, but they're still relatively interpretable. And nowadays we have a lot of deep learning work, and deep learning is very powerful, but it's less interpretable in many cases. There is a lot of work that tries to make deep learning models more interpretable, but it's really in the beginning stages, and I think there's a lot of work to do there. And of course, how much value you need to place on interpretability really depends also on your task and your question. So sometimes you might go for more interpretability, and you might be willing to sacrifice a few % in performance numbers, for example. So at the moment, there's a lot of research in making models more interpretable. And here are two directions that people are exploring. So the first one is called global interpretability, where you try to explain the workings of a full model. So if you have a deep learning model, one way to do it would be to try to mimic this deep learning model with a simple proxy like a decision tree or something else, to just get an impression of what kind of features the model is using, for example, and how these features relate to each other. But a lot of times these models are so complex that it's really difficult to explain them as a whole. So what people also now are looking at is what they call local explanation, where you try to explain a specific output. So instead of explaining a complete model, you're trying to explain why does this model predict this particular label for this text and why not another label. So, for example, local explanation for text could mean just highlighting the most important words, right? So this is a movie review, and the words that are in bold were the words that were the most important for the model to make this prediction. And the model predicted this to be a positive sentiment. But actually, it's a negative sentiment. And so by analyzing or showing which words were important, you can understand why the model made this error. And for some models like linear or logistic regression, identifying the most important words is relatively easy, but for deep learning, it's actually not trivial how to do this. There are different ways of trying to estimate the most important features. One big challenge is that interpretability is not well defined. There are a lot of different definitions, people disagree, and that also complicates how you evaluate interpretability. So there's an upcoming paper by me later this year it's about evaluating local explanations, so the type of explanations that I just discussed, where I compared evaluating them based on automatic measures and evaluating them in a task-based setting. And one of the findings that that is in the paper is that when the model is wrong, so when the model is making a false positive or false negative, these are actually the settings that are the most informative to test whether the explanation is powerful, because then people can't rely on their intuition and they have to really understand the explanation to understand the model. So that was actually all I wanted to discuss. So I've given you a few examples of how we can use natural language processing to help the social sciences, but also there are many challenges left. And personally, I really like doing interdisciplinary research, and I think that's also needed to help bridge the gap between the social sciences and NLP. And that's it.